Hello and welcome.
I see we have Oliver and Khadija in Massachusetts. We have Milo in Kansas, Serafina in North Carolina, Emraya, and Arushi in Seattle.
Joseph, Olivia, Bella, we have a good crew here, Science Mom. Today we are talking about the distributive property, or the distributive law, you might have heard it called.
I'm excited about this one because this one is a patron pick. We asked our members on Patreon, we said we're going to do some free math lessons. What would you like to see? And this was the request. How do you know when to use the distributive property and why does it work?
So we're going to get to that. In particular, we're going to get to what is the distributive property. But before we do, I'm going to shrink down and we're going to look at some solutions. We were given 5, 2, 2, and 1. And I saw Rosalie came up with this top solution. So 5 minus 2 is 3 times, well, 2 minus 1 is 1. So 3 times 1 is 1. So that looks just like 3 times 1, or is 3. I said that wrong. All right, and then another solution that I saw, so Lauren wrote 5 minus 1 minus 1.
Oh, that's a great way to get 3. I like it. Good job, Lauren. And hello to Aaliyah from Houston.
Excellent.
And Tamil from India.
So were there other ways of doing it? I didn't see any others, but I'd be surprised if there weren't something clever.
And I said Tamil, I meant to say Tani. Hello, Tani.
All right, we're looking at a little tiny box there. But that's the problem with shrinking us down small. We're a tiny math dad and tiny science mom.
We are.
All right, so today we do have an activity. We're going to look at the warm-up screen. I'll go ahead and put the code up on the screen where you can see it, but I will also paste it in the chat. It'll just take me a moment, and then you can join our activity and attempt these problems alongside the rest of us. So the warm-up screen that you will see is this one.
Designing a pool, a swimming pool.
Yeah, wouldn't that be fun to have a swimming pool?
That would be. I like to swim.
All right, so in this case, we can't control too much about it, but there is one thing we can interact with here. So there's a red dot. It's kind of hiding there.
I see it. So I can make a big deck and a tiny pool, or I can make a small deck and a bigger pool. That's the better swimming pool, in my opinion, Math Dad.
Yeah. All right. Well, I'm going to open that question up to everyone. What do you notice? What do you wonder? What questions come to mind when you look at this pool and maybe the ability we have there to manipulate it? And yeah, I want to see what you come up with. And I'm going to open up the answers and take a look myself.
Domino wonders, where is Kaladin? Science Puppy is asleep in his little travel backpack. We have a travel backpack for him, and I opened it up so he could get out, and he just curled up inside it and said, no, thank you, I'm going to sleep here. So he's taking a nap.
I think the bright lights sometimes intimidate him a little bit.
Ooh, Emraya says, I noticed that when you cover the floats, they become seats instead.
Ooh, good observation. All right.
So if I drag that over, one float is gone. Now I see 3 floats.
Eli likes the pool more than the deck and wonders if Math Dad will sing the song.
Not right now, Math Dad. Sarah notices the deck chairs and the pool rings appear in a regular pattern. Good job, Sarah, noticing that we have a pattern. Aylin notices adding more deck space makes less pool space. Mariah notices that the pool and the deck can get smaller or bigger and wonders how that works.
Yeah, so this idea of an interplay, you can't have a big deck and a big pool. It's just not going to work with the space constraints. You could kind of share the space between the two, or you could have one big and one small.
And I'm seeing lots of good, I wonder why. Why is it set up this way? That's a good question to ask. And Sarah says, I wonder what this has to do with the distributive property. Me too, Math Dad. Are we going to find out?
Oh, somebody asked it. I didn't even have to pay them any money. They asked it. That is indeed what we're going to find out. So we're actually going to leave the activity behind for a few minutes. Oh.
I want to give a quick shout out to Arthur in the chat. There is a great connection here. 4 lines on the deck, or those little chairs, equals 1 floaty in the pool. So
ooh, that's an interesting theory. Yeah, that maybe one could even calculate the floaties versus the what do we call this? Lounging chairs.
Yeah.
Yeah. Interesting. So it's a kind of a tricky relationship there. All right, I'm going to go back to this screen, because we're going to talk a little about that distributive law, and I'll hide the code, because we want to know what it is, what does it mean, and then we're going to relate it back to that pool problem, and maybe you'll have different things that you know or wonder after we've done our introduction here. So the first thing I'm going to point out is just a notation. What does it mean if I write 3 and then a 4 next to it in parentheses? Because my guess is several of us have never quite seen a number written in this way. So let us know. Type in, is this a number? What does it mean?
Rosalie's on it. Rosalie says 3 times 4. That's exactly what it means.
Yep, 3. This is the same as saying 3 times 4. So as mathematicians are often lazy, we want it the most compact notation possible, and we'll just stick things next to each other if we want to multiply them. Oh, again, yep, the chat's all over this. Oh, Lauren, Goldie, Arthav, yep. So when we stick two numbers next to each other, we're usually multiplying them. Now, of course, if I wrote 34, well, that doesn't mean 3 times 4. That's the number 34 that we know and love. That's why there had to be parentheses up above. But super important idea, if you put two things next to each other, two numbers next to each other, that means we're going to be multiplying them.
If they have parentheses around one of the numbers.
That's right. Good correction there, Science Mom. Okay, so I'm going to draw me a box. I'm going to maybe make it 4 units tall, and how long was that? Let me count. That was 10 wide. But I'm going to chop it up like so, and we're going to just ask, all right, what is the total area of this rectangle? So it's 4 units on this side for a total of 10 on this side. So altogether there are
40 units.
40 units.
Really starting to wonder what this has to do with the swimming pool, Math Dad.
I think you'll figure it out, but I'm not going to make the connection for you. All right,
okay.
So 40 units. Okay, but I also want to point out, here we had one that was just 7 and 3 are those lengths. So what is the area of the first rectangle, the leftmost small rectangle?
The one that's 4 by 7 units?
4 by 7?
That's 28.
This one would be 28. And the other one?
12.
Okay, and you got those just by multiplying, right?
That's
4
right.
times 7 and 4 times 3. So we just found, good job, chat, you're all over this. You found all these different numbers, and we found the area of the big rectangle in 2 different ways. One of them we said was the same as 4 times 10, and the other one we said was just going to be 28 plus 12. So we can break it into smaller pieces, but I'm going to go back one step on both of those equations. I'm going to write the left side as 4 times 7 plus 3.
Ooh.
And on the other side, I'm going to write it as 4 times 7 plus 4 times 3.
Oh, interesting. I like what you did there.
So
And you're saying those 2 expressions are equal.
That's right. They are equal to each other in every sense of the word. And it's just whether we were counting the 2 boxes separately and then adding, or if we were just doing it all at once. And this is an example of what we call the distributive property. And the word distributive, like if you're distributing things, you're giving them out. Well, this 4 is distributing to both numbers that were being added there. So anytime we have some things being added, it's in parentheses, and we multiply on the outside by another number, we have to distribute if we want to get the right value. So that 4 has to distribute to both the 7 and the 3, and that's what we're seeing happening over here. And cool thing is, this is going to work every single time, even if I change the numbers. So let's change our numbers and write out the distributive law. All right, I'm going to make it 3 by 5. All right. And then I'm just going to chop it right there.
I still don't see what this has to do with the pool. but I'm thinking about it.
Okay. Okay, I bet you're going to make some connections here. You will have to use your imagination, but...
Okay.
Okay, so what is the distributive law in relation to this particular rectangle that we've drawn? So that's distributive property. So the total area?
So the total area is going to be 3 times 5, which is 15. Good job, Aaliyah.
Okay, so 15 equals?
And that's going to be the same as 3 times 1 plus 3 times 4.
Good, okay, so we said 3 times 5 is the same as 3 times 1 plus 3 times 4, or I should have written it as 3 times 1 plus 4 is equal to 3 times 1 plus 3 times 4. And did I do it? Did I distribute this 3 to both of the numbers that were being added?
Yep.
Yep, the 3 got multiplied by the 1, and the 3 got multiplied by the 4. Now, okay, so that's with the picture. We see that works. Okay, what if instead of giving you a picture first, just want to make sure we're up to speed here, Science Mom. What if 5 times 2 plus 7, I'm going to hand over the pencil. Can you do this one, Science Mom?
Can I do this one? Help me out if you're watching live or if you're watching the replay. Do it with me. So I need to distribute the 5 into the parentheses.
That's right.
Just like we did before. So that's going to be 5 times 2.
So Leah and Rosalie are already at the answer.
5 times 7. Although I got to fix this math, Dad, because that looks kind of like a plus.
It does.
I was a little sloppy. So there we go.
Okay, so 5 times 2 plus 5 times 7. So that's
5 times 2 is 10, plus 5 times 7 is 35. So it equals 45. Did I do it right?
You did it right.
Woohoo! Lauren and Rosalie and Atharv,
yeah.
Sorry, Atharv, they've got me in the chat. Thank you for the help.
Yes, so I'm seeing people type in 45, and so Aaliyah was the only one that I saw actually type in the distributive property, what it says to do. And so my guess is that some of us just said, wait a minute, that's just the same as 5 times 9, and jumped straight to the answer, which is okay. But we were trying to practice the distributive property, so in that case, I was hoping to see this work here. So that actually brings up a good question. Is there any reason why we wouldn't just want to do 5 times 9? Why would we ever want to do that?
Because you might have something that you can't add together. What if you had a variable? What if it was 5 and then parentheses x plus 2 or something like that?
You read my mind, Science Mom. Okay, so...
But can you read my mind, Math Dad? Can you tell me what this has to do with that swimming pool? Because I still don't get it.
We'll see in a minute. I'd love to increase the suspense. Okay, so variables are values that can... well, they can change what their value is. So we usually use a letter to represent it. So in this case, if I were to chop it up, maybe this one's x, this is 4, and I'm multiplying by 8 over here. So what is the picture here? Well, it's saying that's like 8 times x plus 4. If I wanted to find the entire area, the whole side there is really x plus 4. So we have to multiply the two sides. And according to the distributive law, what do we get? I will wait in the chat for an answer. What is 8 times x plus 4? And whether or not you've ever seen an x before, if you know what the distributive law is,
you can figure this out.
That's right. You just have to do what the rule says to do, even if it doesn't make any sense. And maybe I have stumped them.
I don't think so. Look, Aaliyah and Rosalie have it. Good job.
So the distributive law says that the 8 has to multiply by both of the things that are added. So that's all we're going to do here. We're going to do the 8 times the x plus, and then the 8 times the 4. And then that can simplify to be 8x plus 32.
Nice work, everybody.
Now, what does that mean, 8x plus 32? Well, if we knew what x was, we could just replace it. So if x was 10, then I would just replace the x with a 10, and so it would be like 8 times 14, or if I replaced it right here, I'd get 8 times 10, and then plus 32. So the x is kind of nice because we can sometimes figure out an answer and then plug in different values for x later after we've simplified. But
I think I know what it has to do with the pool deck.
do you?
Well, because if we don't know the width of the pool and we want to change it, it could be a variable.
Oh, science mom, I like it. Okay, so let's go ahead and jump back to that activity screen. So to our warm-up here. So say what you were saying again, science mom?
So I think that if we don't know what the width of the pool is, do we want a big pool or a small pool? If we make the width of the pool a variable, then we can come up with an equation where we'll always know how many deck chairs and how many floats.
Yes, and actually, we're not even going to get into the floats and the deck chairs that much. They're mostly just a cool visual.
What?
But
I've been paying a lot of attention to these decks and pool chairs.
well, it's not that we can't do anything with them, but we're focusing on something a little more basic. We're going to focus on...
And someone asked, can you get an equal number of pool chairs and floats? And I did it, Math Dad. There's 5 on each side.
You did it, science mom. Way to go. Okay, so I'm going to stop the pacing on that screen, and we're going to jump to screens 2, 3, and 4.
So if
maybe.
you are watching the recording, I hope you will get your computer out. If you haven't already, click on that link to the Decimals activity so that you can practice these as well.
That's right, the link's down in the description. But okay, so in this case, you had just dragged it right here, and those numbers are almost hard to read. It says 8.5 feet on the deck, and then 11.5.
So right here, 8.5 feet, and then 11.5.
And then what about the height of the pool?
Oh, that's 18 here on the side.
18. Okay, so given those measurements, can you find the area of the deck? Can you find the area of the pool?
I can. So area of the deck is going to be...
So actually, science mom, that's good. We're going to give them 60 seconds. See if you can answer this one, and even go ahead and peek at the next screen or two.
Do you have music for them, Math Dad? And a countdown?
Maybe.
And yours? Oh good, we're not muted. Yours might look different than the one on the screen, and that's okay.
All right. Okay, science mom, resume. How are you going to find the area of the deck?
I'm going to multiply the width of the deck times the height of the deck. So
Okay.
I have, it's 18 feet high multiplied by 8.5, because that's the width of my deck. So I get 153 square feet.
That's right, and I like that you added the units there. Unfortunately, I didn't put units in this problem, but since we multiplied feet by feet, we're going to get feet squared.
And then I do the same thing, although I did reverse order with width and height, but answer's the same. I do 11.5 times 18 for the pool, and I get 207 square feet. And you know what I like to do in questions like this?
What?
I like to do a quick little sanity check. I can tell from looking at this picture, the area of the pool should be bigger than the area of the deck. And then I glance at my answers, and is that true? Yep, it is. 207 is bigger than 153.
Well, that's kind of clever to do a little sanity check like that. All right, next screen. So on this one, it's different because we're given x and y as the widths of the deck and the pool separately. So how would we get the area of the deck on this problem?
X times 18?
Yes,
Can I do that?
you can indeed.
And good question from Gamerboy. Should we put feet in? Do we want to use units here, or?
Gamerboy, you're a good person. Yes, you probably should, although I don't think the problem will let you, or it won't be happy if you try.
But Math Dad is a fan of using units.
Yeah, in real life, we need units. If somebody asks how tall you are and you're like, 42. 42 what? 42 feet tall, 42 inches tall, centimeters?
42 stories tall?
Yeah, the units actually make all the difference in the world. How
So-
much money do you have? I have 10. Well, $10, 10 cents, 10 banks of money, or yeah.
Now for the total area, I'm going to need to add what I have up there on that length. So I'm going to say parentheses x plus y times 18.
Good, so you did, the total width was x plus y, and the height was the 18.
Oh, and look, it's doing a nice little 18x,
Uh-huh.
18y, almost in slow motion, the suspense. And does it tell me I did it right?
You
It
did.
just,
Oh, I guess you didn't get a confirmation, but that's okay. All right, and then one more screen, Science Mom. So in this one, we're given the total area of the pool as 12 times 3x plus 2y, and in this case, how could we possibly rewrite that? So this could be for a related pool question, or you could ignore the pool and just look at the expression 12 times 3x plus 2y. Is there a good way of rewriting that question?
if you're watching live, help me out in the chat. What would you write? I can also, can we take a look
Thinking
at,
about the distributive property.
can we take a look at answers that have come in already?
All right. Yes, we can. But Joseph says 36x plus 24y. TN, Rosalie, Pascal, yeah, they're all saying that same thing. So 36x plus 24y, where is that coming from, Science Mom?
They're taking the 12, and 12 multiplied by 3, that gives me 36. And then I just leave the x there. And then 12 times 2 is 24. And there's my y. I'm going to go ahead and submit my answer.
So that's the distributive
Ta-da!
law in action. The distributive property. The 12 had to be distributed to both the 3x and to the 2y, and then we just put a plus sign in the middle. We're adding them up.
All right, I feel like this is making sense.
All right, good. We're going to move on to the next screen. So head over to screen number,
Screen number 5.
and 5 and 6. I can do this.
You can do it, Math Dad. Unlock screens 5 and 6.
All right, so on these screens, all we're doing is trying to simplify some expressions. I'm just going to give us 60 seconds or so, see if you can answer the next two screens.
It's the timer that goes zoom from 3 minutes to 1.
So it looks like most people were able to come up with the same answer on this one. So which student is correct, or could more than one of them be correct? Well, we have to simplify. So
let's do this. And then
okay, so the question was, it was -5 times the quantity 6 minus x, then plus 3x. And to simplify this, we're going to take it one piece at a time. We're going to distribute. So the negative 5 distributes to both the 6 and the negative x.
And why do we distribute it?
In this case, we'll come up with a simpler expression. So an expression that's more simple, more easy to work with. So that's usually why you would do it. But another reason is just because the direction said you had to try to rewrite it. So you definitely have to do what the directions say. All right, so negative 5 times 6. I'm going to just write it negative 5 times 6. And then plus, I could do it negative 5 times negative x. And then there's a plus 3x. Well, negative 5 times 6 is negative 30. Negative 5 times negative x is going to be 5x. Negative times negative is positive.
That's
and
right.
Then plus a 3x. Ooh, and now we have negative 30, but how many x's do we have total?
8x.
That's right, I had 5 x's, and now I had 3 more x's for a grand total of 8x. So negative 30 plus 8x is what I came up with.
When I looked at it in my head without writing it out, Math Dad, I thought, oh, student A is correct. I forgot about there being 2 negatives making a positive.
Ooh, yeah, so there was a trap built into this one. So it was student C who got it right?
Yep, student C.
Good job, student C. And then could explain that thought process, but mostly we distributed and then simplified.
Ha, there's my thought process.
Math Dad
told me.
Yeah, okay, that's maybe not a great answer, but we'll accept it for now because we need to move on to screen number 6. In this case, we have a table full of values, and I realize but most of us didn't get the chance to spend much time on this problem, but let's do it together. So in the left column, we're talking about what I called the factored form. So that means not yet multiplied out. And then the distributed form, so that's after we've done the distribution. We've applied the distributive property.
And in the previous screen, we had some good answers. I do like a couple people said it's hard to explain in words, and sometimes it is hard to explain a calculation in words. But Raya said after distributing, you add all the terms together to get your answer. That's a good way to describe it.
Yeah, well, I like Ellie. Ellie just wrote every little step out, just like I had done with my stylus. Ellie typed it all out, and I mean, it's not hard to make it look pretty in that box because it doesn't do math formatting, but good job, Ellie.
And Arthur said marmoset, and Olivia said I simplified. I like that because that's what we're doing.
Ooh, T and S, good. Yeah, you wrote it out really nicely. So excellent work. Okay, so on this one, we start with 5 times the quantity 3 plus 5. So let's not simplify it all the way. Let's just write exactly what the distributive property would say.
Okay, so the distributive property would say 5 times 3
Good.
plus 5 times 5. Whoops.
Get 5 times 5, indeed. So you just multiplied the 5 times the 3 and the 5 times the 5. You distributed it. Okay, next one. Ooh, this one has a minus sign, so what does that mean?
All right, help me out in the chat if you're watching live. Type it in. If you're watching the recording, see if you can do it before I do. You can pause the video.
All right, so the 6 has to be distributed, but how?
Whoops. All right, 6 times 4. I'm confident that is my first step.
Okay.
But then I have a minus, and I'm going to have 6 times 1.
6 times 1, all right. And what do we think about that answer?
18. Looks
Yes,
good.
good job. Rosalie agrees.
Excellent.
That's the way to do it. 6 times 4 minus 6 times 1. Okay, now we're going in the reverse direction. So the distributive law was applied. What was it applied to? What was that expression before we distributed?
This is a puzzle. We get to go backwards. So I see a 3 times something in both of these. So I think it was 3 and then parentheses 5 plus 9.
Good.
Do you agree with me? Is that what you saw too?
Nicely done, Science Mom. You're getting this. Okay, and then, and by the way, it's possible that there were other answers, especially on this next one. There's not just one answer, but what could we possibly factor out? What's the common factor between 4x and 8?
4x plus 8. What did you get for that? I see one possibility. We could do 2
Okay.
parentheses And then it could be 2x plus 4.
Good.
But it could also be 4 parentheses x plus 2.
Yes, both. Both would work. Or for that matter, one could factor out the number 1, although that's not accomplishing much, but it would still work.
1 parentheses 4x plus 8.
Yes. And then when you apply the distributive law, you could multiply everything by 1. It works.
That's true. I guess it does.
All right, but what about the last one? There are two oh, sorry. Never mind. We're not on the last one yet.
Second to last. All right, this one I can do. 3 times 2 is 6x plus, minus 15.
Good, so you did 3 times 2x minus 3 times 5?
Yep.
Okay.
That's what I did.
All right.
Oh, you're right. I was supposed to write it all out.
Yes, you were, but that's okay.
Doo-doo-doo.
We still love you, Science Mom.
Thank you.
All right, and then this last one.
2x plus 4y. I could take out, I could see that you could have 2 in both of those. It could have been 2 times 1 and 2 times 2 over there. So
Right.
2.
Okay, so 2 is being distributed across.
X plus 2y.
That is correct. 2 times x plus 2 times 2y.
Yep. Thank you, Rosalie. Woohoo!
Nicely done, everyone. Okay, we have been working long and hard to get to screen number 7.
With a secret treasure map.
Secret treasure map. Okay, so how does this work?
Long ago, a treasure was buried. The map was chopped into 9 pieces that were mixed up. Your job is to assemble the 9 puzzle pieces by placing them on a grid. I like this problem, Math Dad.
Okay, well, they can't go on it in just any way. They have to go on it so that equal expressions are next to each other. So some of them have been distributive, some of them have not. So like for example, so Science Mom, if you can see my mouse right here, I've got a 4 times x minus 3. To figure out what goes here, we would have to...
We have to find 4x minus 3 somewhere. No, 4x minus 12.
Ooh, so if we distributed, we would get 4x minus 12. So is that actually that's right over here. So I could grab this piece, and then
but I gotta rotate
if
it.
you click on it, it will rotate. And
They're matched up.
all right, so I'm going to give everyone
Oh my
a
goodness.
few minutes to work on this, and then you're going to help Science Mom do it. So
I think this might be a tricky one, Math Dad.
maybe.
have to say, great job. Arushi, Aylin, Arthur, TN, several of you got this pretty quickly. And if you haven't figured it out yet, that's okay. You can pause the video so you have more time, or you can just watch along as we solve it right now.
I made the problem, and I still didn't get it done as fast as some of them. But okay, so we need help, Science Mom. Let's start and kind of work across the top row first. So what goes next to that 6x plus 4 term? And please type it into the chat to help us move along. So next to 6x plus 4.
6x plus 4. So I'm looking for something where there's maybe a 2 is taken out, a 2 is factored out. So that would be 3x plus 2, all times a 2.
Oh,
do you see that?
I think there it is.
Right here.
Yes, so move that one up in place.
I found it. Okay, so right up here I have my 2 times 3, that equals 6, and then 2 times 2 equals 4. So there we go. Those two match.
Okay. Then next to 5x plus 5. Ooh.
5x plus 5.
I see it. It's the 5 times x plus 1.
Oh, there we go. That was sneaky math, Dad. So 5 times x times 1. I'll just turn this one briefly so you can see these two. Do these match? Are those the same?
The two at the top
they are.
match, okay.
Now I need to put them side by side here.
Did
I do it?
No, you messed up the other one.
Ah! Okay. There we go.
No.
Now they match.
Well, this is not good. Oh no, it's a minus sign. Oh no, Science Mom, I've lied.
What's a minus sign?
Times, this is a minus 2.
Oh no, Math Dad, I think you made this harder than you intended to.
Well, I did miss the minus sign. Where in the world was the right answer then? 2 times 3x plus 2. I can do this.
I'm very entertained by this. Math Dad is being challenged by the problem that he himself made.
All right. All right. Back to work then. Okay, so we didn't know this answer and we didn't know this one.
Ooh, I love the comment I just saw from Clark Kent. We did all of the undistributed equations to find the squares. So they did all the math first to match
that
them.
was clever. Yeah, writing it out or thinking about it. All right, so 3x minus 6. We definitely need maybe a 3 times an x minus 2.
Guess what Science Mom Amber said?
Uh-oh.
Math Dad would not make a good pirate.
No.
He can't put together his own treasure map.
The treasure always eludes me. All right, there we go. 3x minus 6 and 3 times the quantity, x minus 2. All right, now.
Okay, so we got foiled at the beginning by that sneaky minus plus sign mismatch, but now we're on a roll. 21x minus 3.
12x minus 3.
12x minus 3.
Okay.
This is really challenging, Math Dad. You have to be able to read numbers upside down.
You do. It takes some patience, but I actually see the answer, Science Mom, right there. Won't that give us a 12x minus 3 if we distribute the 3 times the quantity, 4x minus 1?
Yes, it will.
Okay.
Now, do I need to try and match where this arrow is? I want to look for the 5x minus 3.
Yeah, you could match the arrow, or you could match either side. I mean, that particular square has 3 neighbors that we know.
Okay, so 5x minus 15. Do we see a 5x minus 15? I do, right up here.
Okay.
I'm going to drag it down in. And you know what else occurred to me, Math Dad? It's pretty tricky for people to give feedback on what to do because...
It is. I had kind of envisioned that they would tell us what numbers to look for, but yeah, it's not an easy one to give feedback on.
Oh, Leah says, I am the pirate because I am solving the puzzle. I like it. All right, we have 12x minus 7. I don't know.
So 21x minus 7.
21. Now I can think of something that would match with that.
Because to get to 21, you're usually going to have to use 7 times 3.
Yes. So
okay.
If I can find 3 times quantity 7x minus 1, that would work. Do I see a 3 in a parentheses? Oh, but I see
that's
7.
The one. That's what you meant, yeah. 7 times 3x
1.
minus 1. All right.
So I'm going to turn it this way because then it'll match right here. I'm going to drag it in.
Okay, those match.
Okay, we're just down to 2 left. We are so close. 6x minus 4, that could match with, I could take out the 2. So 2 times quantity 3x minus 2. Do I see? Oh, 2 times 3x minus 2. I found it. I'm going to turn it around so this one will match here. And then I have to check, does this match this? It does.
4x plus 4,
A very good sign. And now I can't just drag this in any which way I want. I have to make sure it lines up. 3x minus 3 times x minus 3 is the same as 3x minus 9. So do I have a 3x minus 9? I do.
Okay, drag it into place. Submit your answer.
Cross my fingers.
And look what those arrows.
It worked!
They do indeed reveal a path to the treasure.
Gamer Boy says my name has just been upgraded to Pirate Mom. I love it.
All right. Well, that was a little harder than I thought. I'm going to...
But can we just give shout outs super fast? Look at this. Aylin, Maria, Olivia, Joseph, Emrea, Alicat, TNS, TN.
Oliver, Tharv, Rosalie, Bella, Arushi, Gamerboy, Clark Kent, yes.
Good job. And if you need a little bit more time, that is okay, because this was so challenging, it even stumped Math Dad for a few minutes.
Yeah, lots of places to go astray on that one. All right, let's take a look at our next screen, Science Mom.
That was a fun way to practice the distributive
Good.
property. I liked that one.
So this one is expert level, meaning I haven't taught you how to do it yet, but maybe, just maybe, you can figure
Don't you need to open it up
out.
for them?
It's open and available.
Oh, it is open.
Yeah.
Okay.
So how in the world would the distributive law work if there were multiple things to distribute across or to be distributed? And I was going to draw it all out and make some pictures, but I think I'll just reveal the answers here. So what is that? Well, 4, it just has to be multiplied by everything. So 4 times 3 plus 4 times 6 plus 4 times 9 plus 4 times 5. So the 4 has to go to each of the numbers that's being added.
92.
All right. What about if there are variables?
We just do the same thing. So that A is going to be multiplied by everything.
That's right.
A times X plus A times Y plus A times Z.
Yep. And that's how we write it, which is AX plus AY plus AZ.
Mm-hmm.
And then, this last one, this one was going to be trickier because if you actually wanted to draw it out, your grid would look something like this. So we had A plus B, and we had X plus Y. So you'd have to chop it this way, and you would get AX, XB, AY, and BY. You get 4 different terms. So they call that foiling, or just sort of distributing. So that's something that you'll get to when you are in, maybe in a pre-algebra class, but definitely in an algebra class. You will learn that and become
Can I
ninjas.
show something? Do you know what I want to show?
You want to show the foil crab?
Yes, the foil crab.
Okay, show the foil crab.
So I remember when I was in school, I liked to doodle on my papers and draw little cartoons. And one time when they were saying, okay, you need to times each term by all the other terms, I took the A and times it by the X and then by the Y. And then I did the same thing with the B. And then I thought, oh my goodness, that is the claw of a cute little crab. And forever after, when I had math homework, I would draw little foil crabs anytime I had to distribute. And they made me smile. There you go.
Now you know the foil crab.
Now you know the crab. Yes.
All right, and then the last thing we were going to ask is just, how did you feel about learning today? So how well do you understand it? And how did you enjoy it? How did it make you feel as we were going over this? For some of us, it was a new topic. For others, this was totally review. And I want to try to do something cool here. Maybe I can succeed.
You can do it, Math Dad. Pascal says, so fun. I love that feedback. Oh, we have a distribution forming.
That's right. I'm going to zoom in, and I'm even going to show what my screen looks like here, what I can see. So I can see so individual answers that are coming in, but I can also see where people drew. Some were to the right, some to the left. But I'm really happy to see that most of us had a good time learning today, because
It's all thanks to the pirates and the crabs.
You stole me treasure. Arr. All right.
This is great. We have to see if we can get Science Puppy up here real quick.
All right, Science Puppy here to say goodbye, and I'll give some shout outs and wish everyone the best. See Sarah, Arthur, Maria, Joseph, Olivia, Alicat, Ellie, Ruby, We've got Rosalie,
There we
Goldie
go.
and Ellie, Pasquale, Bella, Harushi, Gamer Boy, and Clark Kent. We will see you for more mathematical adventures in the future. Until then, work hard and grow smart.